Hello and welcome to section 2.1. Today we're talking about integer exponents, and in doing so we're going to be reviewing just a little bit about what exponents are and how they work. So to start here, I just want to look at this table and kind of see what's going on, try to figure out what we're looking at here. So I'm going to look at the values first. So I see 625, 125, 25, and 5. And I'm sort of trying to figure out how we progress in that list. And I'm kind of banking on things that I sort of know is some easier results. I know that like 25 is 5 times 5, and that's what 5 squared means. It means 5 times 5. And obviously 5 is just 5 by itself, or 5 times 1. And then we think about what the exponent part means here to give me 125. That's 5 times 5 times 5. And 5 to the 4th, which is 625, is made from 4 5s being multiplied together, because that's what exponents mean. They mean multiply that number by itself that many times. We could see the same thing as we look at the 4s and the 3s, and sort of what the pattern is that you see is kind of on you and more specific to you. But as I go from right to left on the 5s, I notice that every single time I'm taking away a 5. I would say the pattern that I see is I'm sort of taking away, I'm going to put that in quotations. I'm going to take away a 5 as I move right. Okay. And we'll talk about what I mean by that taking away in just a second. The next one says, what do you see? What pattern do you see with the 4s and the same thing with the 3s? Okay. Again, I know that 4 to the first power just means I have 1 4 there. 4 to the second means I have 4 times 4. 4 to the third is 4 times 4 times 4. And 4 to the 4th, I have 4 4s. Okay, and when I multiply those strings of 4s together, I do know that 4 times 4 is 16. You could do some work to look at 4 times 4 is 16, times 4 is 64, and the same thing with 256. But I mean, that's a big number, and we might not know that right off the top of our head. But again, I kind of see this idea of taking 4s away from my list of multiplication. And so we could kind of think of that. I'm going to slowly work our way to what's actually happening here is, we're writing one less 4 in each column, as we move right. So as we move our way to the right, we're writing 1 less 4. And then let's look at the 3s. So for the 3s, we do see the same kind of thing happen. This is 3 times 3 times 3 times 3. And then we have 3 times 3 times 3. And then 2 of them multiplied together. And then just 1 of them. I don't know why I wrote a 2. That should be a 3. So what's another way that we can look at how that's actually happening? How do I undo one of my 3s that's being multiplied? Okay, the way I would say we undo multiplication, or the opposite of multiplication, is division. So I'm going to divide by 3 each time we move right. Okay, and that's sort of the main idea of this, and that's what we're actually doing. Mathematically, that's what we're doing. The top answer for the 5s is not incorrect. It's just more of an observation. It's that I took away a 5 from my list of 5s and my multiplication. And that's great. That's a great way to visualize it. But mathematically, what we're actually doing is every single time, if I look at 625 and I take this step to the right and I divide by 5, I'd get 125. Now maybe I don't know that. Maybe I don't know that off the top of my head. But as I work my way down, I do know that 25 divided by 5 is going to give me 5. So we kind of, how do I say this? We kind of justify our thought process using mathematics. So in order to complete this table, because they just kind of left us hanging for 5 to the 0 and 5 to the -1, 5 to the -2, as well as the 4s and the 3s. So how do I complete this table? Well, I'm just going to keep doing the same thing. I'm going to divide by 5. I'm going to divide this answer right here by 5. 5 divided by 5 is 1. If I divide by 5 again, 1 divided by 5, you could do it on a calculator and get a decimal. I'm going to stick with fractions, is 1/5. 1 divided by 5, that's how we would write that. And then if I divide by 5 again, that one's kind of weird, but I would really have 1/5 divided by 5. And if we think of our keep, switch, flip, and where we keep the first fraction, change it to multiplication, so 1/5 times, and then we flip this second one, we flip 5/1. So this is a little bit of a review on how to divide fractions. That's always fun. And if I look at doing that, and then remembering multiplying fractions, which is another tricky part. 1 times 1 is 1, and 5 times 5 is 25. So I get 1/25. Okay. Let's keep that going. 4 divided by 4 is 1. 1 divided by 4 is 1/4. And then for the tricky one, 1/4 divided by 4, or 4/1, is 1/4 times 1/4. 1 times 1 is 1, over 4 times 4 is 16. So I have 1/16. Take a second and see what you think you would get for the 3s. You can pause the video if you need to. Okay, hopefully you had a chance to do that. As I continue my process of division here, I should get 1, 1/3, and 1/9. Now the trick here is, the main idea out of this is that we see some recurring numbers. Now we might see them in different locations, but I see the number 3, and 3 is a bad example because it's kind of everywhere in this row. But I see the answer being involving a 3 here and here. I also see a 9 here and here. So that's got to be meaningful somehow. Let's see if it keeps that same idea. I see a 4 here, and I see a 4 here. and then I see a 16 right there, and a 16 right there. Okay, so we're kind of seeing this kind of a mirrored image, but involving fractions. I see a 5 here, and a 5 here. And then I see a 25 here, and a 25 here. So really what that means is as I go with negative exponents, something relating to the positive exponents is happening. But I think we're going to get to that in just a little bit. So I'm just going to make you think about that a little bit. So here we want to think about general rules, because everything in math we want to get to some kind of a rule that we can then reuse. And this rule for writing, the rule that we're trying to write for a to the 0 power. Anything to the 0 power, what did that end up being? Well, that happened right in here. My 0 powers happened right here. And what did we get every single time? 5 to the 0 was 1, 4 to the 0 was 1, 3 to the 0 was 1. And in math, a lot of times we come up with rules by noticing patterns, and that's a pattern. Every time I raise something to the 0 power, or took away one of those numbers that we were multiplying by, I was left with a 1. So I would say that a to the 0 power, oh boy, oh, that's my problem. There we go. I would say that a to the 0 power is going to be equal to 1. Any number to the 0 power is going to be 1. That's a pretty big thing. I'm just going to throw out there that 0 to the 0 power might be a little bit of an issue. But everything else to the 0 power we're pretty confident is 1. Okay, then it says to write a rule for a to the negative n. And this is what I was trying to make you think about earlier. I could rewrite these. Let me just give myself a little bit of room. I could rewrite each one of these in a very special way. 25 is 5 to the 2nd power. So this would turn into 1 over 5 to the 2nd power. 16 is 4 to the 2nd power, so this is 1 over 4 to the 2nd power. And 9 is 3 to the 2nd power, so this is 1 over 3 to the 2nd power. Now that's important for a very special reason. This 2 carries over to be right there. This 2 carries over to be right there. And this 2 carries over to be right there. So what we do when we have a negative exponent is we keep that exponent, but we put it in the denominator. So we write it as 1 over. So the quick trick is to write 5 to the negative 2 as 1 over 5 to the 2. And you could figure that out as 1 over 25 if that was more helpful, but the basic rule that we'll follow is a to the negative n is going to be 1 over a to the n. And that goes for any number a. Again, 0 might be an issue, but any number a and any value n. Let's look at some more properties of exponents here. So I've got 3 written being multiplied 1, 2, 3, 4, 5 times. Okay. So our basic rule of exponents means that I can then write that as 3 to the 5th power, because there's 5 3s. 1, 2, 3, 4, 5. Here we have something a little bit different. We have parentheses involved. So if we remember order of operations, we have to do parentheses before we do anything else. So let's focus on those parentheses first. I have 1, 2, 3, 4 3s in the parentheses. So this part turns into 3 to the 4th. And then here I have one 3 by itself. So we would say that's 3 to the first power. And that's something that's kind of important with exponents that we never really think about. Any number that we're given, say it's 5, 10, 30, whatever, is really just that number to the first power. But then if I get rid of the parentheses, if I kind of forget about them, I really just have 5 3's being multiplied together, because parentheses don't hold a whole lot of weight in just multiplication. No matter what I do, I'm going to do this from left to right if I'm calculating it. So I have 5 3's, so that's 3 to the 5th. And we're just going to reinforce that with another example here. In the first grouping of 3's, I have 3 of them, so that's 3 to the 3rd. In the second group of 3's, I have 2 of them, so that's 3 to the 2nd. But if I get rid of the parentheses, I just again have 5 3's being multiplied together. Okay. Let's go ahead and look at, so what pattern do we see when we multiply two numbers with the same base? So this kind of brings us into some vocabulary stuff where we're dealing with exponents and we need some names. The number that's on the bottom in an exponent expression, so I have, like here, our big one was 3 to the 5th. We never actually figured out what that was, but we could. Just grabbing a calculator, 3 times 3 times 3 times 3 times 3. Is that 5 of them? I think so. Okay. So we get 243. So it would be nice to have some names here. This number on the bottom, that's kind of holding up the 5, is called our base. The power that we talk about, the number that's written up above, is called the exponent. I would say that power is acceptable here, but it's kind of, kind of watch your verbiage. It's not like, you don't always want to say that the power is 5. You might want to say that the exponent is 5 if it fits better in the sentence. And then as far as the number out here, since it's a string of multiplication, we would say that it's the answer to a multiplication problem, which we call the product. All right, so we have base, exponent, and product. Those are the 3 key words. So what pattern do you see when multiplying two numbers with the same base? So the base in all of these was 3. And then we kind of split it up into 2 versions of multiplying those exponents together. So here I had 3 to the 4th and 3 to the 1st, and somehow that became 3 to the 5th. The same thing happened when I had 3 to the 3rd times 3 to the 2nd. So how do I get 5 from these two numbers? These two groups. I don't like that color on that. Let's just use yellow. How do we get 5 from 4 and 1, giving me 5, and then 3 and 2, also giving me 5? Go ahead and pause the video and think about that. Okay, hopefully you had a chance to think about that a little bit more. But what we end up with is we really just added the exponents. Okay, that's what we ended up doing, is in order to get 5, 4 plus 1 is 5, and 3 plus 2 is 5. So let's see if that pattern works here. Let's see if that idea works. 5 to the 2nd times 5 to the 5th should be 5 to the... If you know it, go ahead and write it. If you don't, you can always split this up. I have my 5 to the 2nd times my 5 to the 5th. And how many 5s do I have in total? Well, I have 7 of them. So kind of the idea there is that when we multiply two things that have the same base, looking at this portion right here, these two values have the same base, we add their exponents. For this one, we're looking at some division. So I have 4 to the 5th, and this is, way too small, really, but 4 to the 5th divided by 4 to the 3rd. So what happens when I have that? Well, they kind of do that thought process for us. They write out our 5 4s and our 3 4s, and then we kind of do some cross cancellation, right? I can cancel these two and these two and these two. And that leaves me with 4 times 4, which is 4 to the 2nd power. So what pattern do you see when dividing two powers with the same base? Well, how can I get from my original problem to give me 4 to the 2nd power? Well, I noticed, and so the question is, how do I turn 5 and 3, how do I turn those two numbers into 2? For me, I'm thinking subtraction. So we would subtract the exponents. All right. So let's use that same idea to figure this one out. Well, if it works, we're going to assume it works, then we're going to check it really quick. So I would subtract the exponents. 8 minus 3 is 5. Let's see if that works right up here. So I have 8 6s times 6, 7, 8. And on the bottom, I have 3 6s. I'm going to leave them over to the left so that they're a little bit easier to cancel out. Oop. Gotta hit them when you try to cancel out. 6s, 6s, 6s. And then what am I left with on the top? 1, 2, 3, 4, 5 6s. So we're good to go. And I will try to change colors a little bit more often. I know I get kind of stuck with one color. All right, so let's go ahead and look at this next one. So this is a whole different rule. It says complete the following equations. 5 to the 3rd squared. So 5 to the 3rd, it looks like 5 times 5 times 5. And we want to make sure that we square that. That's what our problem says to do. Squaring something means to write that twice, right? So it's going to be that number times itself. The only trick here is that number we have to think of as this whole 5 times 5 times 5. So we write that twice, being multiplied together. And how many 5s do we have? 1, 2, 3, 4, 5, 6. So how can I turn a 3 and a 2 into a 6? So I look back at my original problem equation and my answer, and how do I relate those? So what do you see when raising a power to a power? That's what's going on here. I have 5 to the 3rd being raised again to the 2nd power. Well, the only way I know to get 6 from 3 and 2 is to multiply. So we will multiply our exponents to get our result. We'll go ahead and do the same thing on this one. It's going to get a little bit long-winded, but it's valuable to see that in action. What do you think you're going to get when you go 7 squared to the 4th power? If we follow that idea of multiplying exponents. 2 times 4, I'll write that here, 2 times 4 is equal to 8. Let's see if that works. So I want to do 7 times 7, which is 7 squared, to the 4th power. The beauty is I have to write 7 times 7 4 times. I know some of those look like minus signs, but they are all multiplication. So how many 7s do I have now? 1, 2, 3, 4, 5, 6, 7, 8. We were right. That's awesome. All right, so we kind of set them as we went through this, but you know, just writing the general rules here. If we're multiplying things with the same base, so both of these are a, and they have different exponents. They could be the same exponents, but what did we do in part A is we added the exponents. So I'm going to say that this is equal to a to the m plus n. So we're adding those two exponents together. For the division problem, we subtracted. So we get a to the m minus n. And we showed you in the example that the top one was always bigger than the bottom one, but it doesn't have to be that way. The top one could be smaller than the bottom one, and it would still work out just fine. Write a general rule for a power raised to a power. In that case, we multiplied the exponents, m times n. Okay. So here we see a couple examples. And now I know that there's some other operations here. It's not all multiplication, but we can still use our ideas of exponents in order to get this right. So looking at this problem, we go 5 minus 2. That gives us 3. And at the same time, we did 5 plus 2. Which gave us 7. So we worked with parentheses first, following our order of operations, PEMDAS. So we did our parentheses first. Exponents come second, and so we can do any operations with exponents that we need to. So I have a 3 to the 5th, and a 3 to the negative 8th. Don't let the parentheses around the numbers freak you out in any way. It doesn't really change much. Okay. But since I have multiplication is telling me to add those exponents. I just wrote that up above. So I want to add those exponents. 5 plus negative 8 is going to give me negative 3. And at the same time, since there was a plus sign kind of separating this stuff, I dealt with this this 0 exponent here. Anything to the 0 power is going to give me 1. Okay, so I have 3 to the negative 3rd plus 1. Since 3 to the negative 3rd is 1 over 3 to the 3rd, and 3 to the 3rd, sorry about that, and 3 to the 3rd is 3 times 3 times 3. And 3 times 3 gives me 9. 9 times 3 gives me 27. I have 1 over 27 plus 1, which is just 1 and 1/27. Okay, now for another problem. I know this feels like we're doing order of operations backwards a little bit because every time we add or subtract first, but that's because they're inside the innermost parentheses, so we have to start with that. So we're starting in these interior parentheses. 3 plus 1 is 4, and then we also have some parentheses in the bottom, and then you also kind of have to remember that any time you have a fraction bar like this, that's sort of a hidden extra set of parentheses on the top and on the bottom. I need to turn those off. Oop. Don't get rid of that. So hidden parentheses on the top and on the bottom. So the 7 minus 3 is 4 as well. Okay, so I have 4 to the second raised to the third power over 4 to the second. Since I have the power raised to a power here, that's kind of the third rule that we wrote. We multiply those exponents. 2 times 3 is 6. And then, so I have 4 to the 6th over 4 to the 2nd. And that, since I have that division tells me to subtract. With that division telling me to subtract, 6 minus 2 is 4, 4 to the 4th. We wrote that on the first page as 256. Okay. Go ahead and pause the video and try these two your turn problems. Use the above two problems as guides. I really hate trying to do those your turn problems on the very little space that they give you, so I would recommend using a separate sheet of paper to do that. I have the ability just to get a new slide here, and that's what I'm using. So again, we want to start with our innermost parentheses, and that's going to lock us down to dealing with the subtraction and the addition here. So let's try to figure this out. 6 minus 1 is 5, and I'm sort of going to build this from the inside out here. So I have 5, this squared, and then those square brackets they give us, which is just another set of parentheses, squared. On the bottom, 3 plus 2 is 5, and this is to the third power. Okay. Now I'm thinking in the top, I'm sort of thinking this is power to a power. Okay, and that means that I want to use my power to the power rule, which tells me to multiply these two. 2 times 2 is 4, and I'm just going to rewrite the bottom. Now I'm thinking again that I have division, and division tells me that I want to subtract my exponents. That was another rule that we wrote down. 4 minus 3 is 1, so I get 5 to the first power, which equals 5. It would be really hard to fit all that onto that one line. Let's look at this one here. And let's see what we can do in our kind of first go-around. So I'll deal with parentheses first. And the sad part of that means that I have to write everything else that I'm not doing. Okay, so these parentheses right here, I could have figured this out as 2 to the second power, but I'm going to leave my answers kind of with exponents. No, I'm not. I lied. I'm going to deal with that first. It's kind of up to you, but you'll see why it's important here in a second. So 2 to the second power is 4. Okay, dealing with these parentheses here, 10 minus 6 is another 4, and that's to the third power. And here I have 4 to the negative fifth power with a multiplication there. So let's deal with our multiplication next. So I can get rid of these parentheses out here. I'm not really changing this. I'm just rewriting it a different way. That's 4 to the third power minus. Here I have 4 to the third power. I'm actually going to rewrite that. 4 to the third power times 4 to the negative fifth. And with that, that's a multiplication. Multiplication told us that we wanted to add our exponents together. 3 plus negative 5 is going to give me negative 2. Okay, and now I'm kind of stuck because of the subtraction in that I should probably figure out what these are. I do have them on the first page. You could go back and see what those were. 4 to the third power is 64, and 4 to the negative second power is 1 over 16. And so to get a single answer for this, it's not pretty at all. I'm taking 1/16 off of 64. So we're going to have 63 and 15/16. That step right there, you could look at it a couple different ways. It's not a great step, but you know, if you, as far as working with exponents, there was no working with exponents that happened here, and that's our main goal for today. All right. So hopefully that helped. Show up to class tomorrow, and we will iron out any other details that we need to, and we'll also look at some other practice problems. Have a good day, and we'll see you in class.